Okay, good afternoon. It's time to start. And as you can see very clearly, the title of Penning Hall is Comments on Trapping Horizon.
I'd like to thank the organizers for their kind invitation. Today I'm going to talk about trapping horizon. So this is the panel diagram for a classical black hole. Here's the event horizon. But then Hawking introduced Hawking radiation, so he claims that the black hole would eventually disappear. And then you still have the event horizon. In both cases, the event horizon is originated from the end of the singularity. Without the singularity, you probably would not have event horizon. So nowadays, people tend to think that with the UV complete theory, there is no singularity, and the Penrose diagram should look like just the same as the cosmic space. But then you would probably have a trapping horizon. This yellow line depicts a part of the trapping horizon, replacing the notion of event horizon. Now you may still have a high curvature region replacing the singularity. You have collapsing matter, and the standard story is that the collapsing matter collapses inside the trapping horizon with positive energy going out as Hawking radiation, and you also have negative energy going in. So the standard, the conventional theory is that the negative energy is coming from the vacuum energy. It continues coming inside, so that the total energy under the trapping horizon reduces over time, so that the black hole looks like smaller and smaller. The Hawking radiation is originated somewhere away from the outside the trapping horizon, so there is no chance of it taking information from the collapsing matter, which is well under the trapping horizon, unless you have no local interaction. So I like to talk about a few properties that we found about the trapping horizon in this talk, and we will not talk about event horizon. We will only focus on the time before this dashed line, so early enough in time, so that even if you believe in some event horizon or singularity, it doesn't matter. I would just be focusing on the earlier part of the evaporation. So in this talk, when I mention horizon, from now on I would mean trapping horizon, not event horizon. Apparent horizon is just a time slice of the trapping horizon. So in the conventional story, you have collapsing matter, and with negative vacuum energy, the size under the horizon could be larger. So it looks like there is a local minimum of the surface area over here. When you have negative energy pumping into the horizon, the total mass is getting smaller and smaller, so from the outside, it would look like the neck is smaller and smaller until it goes to zero. Or maybe it stays a small size, and then we would say that it's a remnant. Once under the neck would stay there because it's essentially frozen by a huge redshift factor, so they would look like not moving. And then all the information of the collapsed matter stays under the neck in the bag. They call this the Wheeler's bag of gold. So it stays there. So although the information seems lost from the perspective of observer outside the horizon, but the information is still inside. So in some sense, there is no information loss. But nowadays, people believe in holography and so on, and we found remnant problematic in quantum field theories. So still, this picture is not very satisfactory. Now, in order to change this picture to another picture like this, so that the whole thing evaporates, and then the collapsed matter also comes out, all the information comes out. In this way, you don't violate the holographic principle, but what you would need is something to interact between the vacuum around the neck and the matter under the back, so that it's possible for the information to come out. Now, the standard story is that if you are falling in from large distances, you always feel like you are in an inertial frame, so you wouldn't feel much interaction with anything else, so you would just stay down here. There's no high energy event, so there's no chance for this to happen. It would be more like this picture. So in order to have this picture, you need to have some drama at the horizon. You need to have some high energy events to introduce interactions, high energy interactions between the collapsed matter and the vacuum around the neck in order for the information of the matter to come out. So basically, let me review the situation again. You have matter falling inside the back, under the neck, under the apparent horizon, and you have continuous negative vacuum energy that becomes macroscopic over time, so that when you say the black hole is completely evaporated, what you really mean is just that there is an equal magnitude of negative energy from vacuum going inside the horizon to cancel the positive energy of the collapsed matter. And in low energy effective theory calculation, there was no high energy event identified around the horizon. So the collapsed matter feels like they are just in inertial frames in free falls. Nothing's happening, so there is no reason for anything to take out the information. So there's no chance of bringing out the information of matter. So in this way, you probably get a remnant, but it's not a favored scenario. So I'd like to consider more carefully what's happening around the apparent horizon. And we have always the following assumptions. Firstly, we assume that the semi-classical Einstein equation is valid. So in addition to the classical part of energy momentum tensor for the collapsed matter, you also have a quantum field which would account for the Hawking radiation. So you pick a quantum state for the quantum field, you would have the vacuum expectation value, sorry, the expectation value of the energy momentum tensor for your choice of quantum state and your choice of quantum field theory. We assume for simplicity spherical symmetry so that your metric can always be written in this way. We will always write it down in this way. So here you have U and V, which are combinations of the time and radial spatial direction. They are both light-like. One of them is ingoing, the other outgoing. The coefficient will be called the function C. And we will choose the convention such that the coordinates U and V are chosen to agree with the Minkowski coordinates, Minkowski light-like coordinates at large distances in the asymptotically flat region. So that C goes to 1 at infinity. And this R is called the areal radius, so that on the sphere of given values of U and V, you have a sphere with a surface area that would always be given by 4 pi times r squared. So this r is called areal radius. It's not the same as the distance from the surface of the sphere to the origin. And also we will assume chanting horizon in this talk, so this is not the talk about KNY model like I did a few years KMY model, there is no trapping horizon. Here I'm talking about a conventional model where you have negative energy and trapping horizon. And we just investigate, according to Einstein equation, what's happening around the horizon. So what's the definition of trapping horizon? With this kind of metric, with the aerial radius, the trapping horizon is defined as follows. Firstly, in Minkowski space, usually when you go out or go in the light cone directions, the aerial radius should increase and decrease. But it may happen that in part of the space-time, in both directions, the aerial radius is decreasing. So when you have a space-time with a neck, with the bag-like structure I showed earlier, around the neck, the aerial radius is increasing, and a little bit under the neck, it's decreasing. So that's the trap region. You are going in both ways at the speed of light, but you always feel like the size of space is shrinking. So you're not really trapped, you just feel like trapped. And then the boundary of the trapped region is called the trapping horizon. So on the trapping horizon, since the derivative of u is always negative, it's the derivative of v, the derivative of v that changes sign. So on the trapping horizon, the derivative of v of r is 0. So v is this light direction, u is this one. And also, your second derivative of r is also fixed by the geometry. So this is the Penrose diagram. The trapping horizon, being the boundary of the trapped region, has to be a closed surface. And also, the origin is always the minimum value of the aerial radius. So this cannot cover the region. So it has to look like that. And we were saying we were focusing on the space-time under this dashed line. And you have collapsing matter shown in shaded blue. And outside, we assume that it's in vacuum. So outside the trapped region, derivative of v is positive, inside is negative. And the part of the trapping horizon that showed up earlier is called the outer trapping horizon. And you have negative energy going in vacuum over here. Over here you have positive energy of the matter. So that's the basic picture. And of course you also have Hawking radiation outside the trapping horizon. So the first comment, part of this is just review. First of all, you can easily show using Einstein equation that you must have negative energy. Without negative energy, it's impossible to have trapping horizon. And also, if you want to have this topology, that this trapping horizon turns around over here, then you must have some drama, meaning that the vacuum energy momentum tensor would be very large for free-falling observers. Otherwise, this part of the trapping horizon would always be time-like. It cannot turn space-like. It's easy to see from Einstein equation that in order for the trapping horizon to turn space-like, you have to have a large energy momentum tensor at the horizon. So on the other hand, if you assume there's no large energy momentum tensor for free-falling observers at the horizon, then we identified a gauge invariant quantity, which is at the Planck scale in the trapping horizon. So that's what I like to show. So in some sense, assuming no drama gives you some drama at the horizon. So this is the Einstein equation for the spherically symmetric space. Did you have trapping horizon, on the trapping horizon, derivative of R with respect to V vanishes. So you see that some of the equations give you very simple relations among the energy momentum tensor and derivatives of R. So using that, it's easy to write down the second derivative of R in terms of the energy momentum tensor. And also, this is the derivative of the V coordinate of the trapping horizon. So this tells you the direction of the trapping horizon. So initially, in order for you to have a trapped region, you must have second derivative of R positive, which means that TBV must be negative. So you must have negative ingoing energy flow. And then in order for this to turn from time-like to space-like, you need the numerator to vanish and then change sign. But for it to vanish and change sign, it implies that this quantity, this part of the energy momentum tensor is actually very large for free-falling observers. So furthermore, if you consider the following quantity, the quantity you consider is, if you imagine you're an observer staying on top of the trapping horizon, then the energy momentum tensor you observe in vacuum would be like a light-like energy flow with a magnitude which is very large. This is the Planck length. And it always gives you a total rate of negative energy of this amount, 2 pi over Planck length squared. Here, this is not just the order of magnitude. This is actually just a precise, not precise, but approximate number. So it's actually an interesting, robust result because you can imagine doing all sorts of experiments outside the horizon. You can throw things into it. You can go in and come out because this is time-like. Doing things would change the location of the trapping horizon. However, the energy momentum tensor observed on the trapping horizon would always be like this, no matter how much energy you throw in. So an interesting question is whether this gives you some possibility of modifying your low energy effective theory because you have high energy gauging varying quantity appearing at the horizon. But so far we have not yet found a way of writing down low energy effective theory naturally to be sensitive to this gauging varying quantity. So that was the first comment I'd like to make. This is the second comment. The result, I don't have much time, so let me just give you the basic picture. So the conclusion is that when you have a black hole evaporating to a very small fraction of its initial mass, like a tiny fraction of this order, throughout all this time, although the collapsing matter has entered the horizon for a long time, for a time of order Schwarzschild radius to the third power, but the surface of the collapsing matter would still be just at a Planck scale distance from the trapping horizon. So you wait for the black hole to evaporate for a very long time. The black hole is now like 1/100th of its initial mass, but the collapsing matter is still only at the Planck length distance from the horizon. Now, this doesn't look like quite consistent with this picture because you see collapsing matter here, the orange line, and the apparent horizon, the blue line here. The apparent horizon is expanding, right? And collapsing matter is shrinking. It should look like the distance between them is increasing over time. But actually, the matrix in between is also shrinking over time. So it's a little bit like the opposite of inflation. So inflation is like you are sitting there, I'm standing here, we're doing nothing, but our distance is increasing over time. This is like I'm running this way, you're running the other way, but distance in between us is space is shrinking between us, so we never really get very far and separated. So here, the orange curves are constant R curves, and the green curves are constant U curves. And I plot them in a different way over here. So these are the blue curves. Somehow they are not the same blue. Sorry, they're green. And okay, so this is the tracking horizon, and it's over here. So the area, the volume we're considering is this part. And it's shaking. So it's this part. So the collapsing matter goes here, tracking horizon here. I'm saying this distance, any distance in any type of space-like direction, however you draw it, would still be just Planck length. So the assumptions we made are also the no drama assumption that the energy momentum tensor is small for free-falling observers on top of the horizon. The way we derived it is using just a semi-classical Einstein equation. But let me skip the derivation. We just say that the function c, which determines the distance in radial direction, is found to be in some exponential form. So that is why the distance is shrinking between two given points. And so over here, I mean, if you choose a light-like direction, of course the distance is 0. So I should have chosen a space-like direction. So then you naturally ask, so how is it different from having no trapping horizon if the thickness of the trapping horizon is Planck length? Another question is, eventually something would happen in order to make a closed circle for the trapping horizon. So according to the firewall story, what's happening is that you get the firewall, so you have a high energy momentum tensor, so it's possible for the trapping horizon to turn around. And so the next comment about trapping horizon I like to make is that we studied the en-route vacuum outside, around the horizon and outside the horizon. And we ask what happens if you observe a Hawking particle outside the horizon. So you're outside the black hole, and there's a particle in Hawking radiation, and you measure a particle. It's going to induce a collapse of the wave function of the en-route vacuum. And the conclusion is that there would be induced particles in the en-route vacuum, and that would give you high energy particles on the horizon, which is the firewall. And then, combined with our previous result that the collapsing matter is still almost on top of the trapping horizon, this Hawking induced particle with large energy is just on top of the collapsing matter. So there could be high energy scattering between them. So the picture is like this. The en-route vacuum is defined as a Minkowski vacuum of the infinite past. So you have Minkowski vacuum here, and then the ingoing modes follow these lines, and then they pass origin, they become outgoing modes like that. So in a light cone frame, you say that this is a constant time curve. I don't think my hand is shaking somehow. Okay, so this is a constant time. So it evolves with time this way. So the Hilbert space of one particle is the space of functions on this segment. Goes that way. So when this system evolves through this collapsing matter, you are in the Schwarzschild regime. You get en-route vacuum. This is en-route vacuum. Now, because of the space-time curvature, the result is that if you have equal spacing here, the spacing here is exponentially different. So that's why the notion of particle is different from here and here. So the en route vacuum is a vacuum state for free-falling observers, but it's a state with particles away from the horizon. And our question is to carry out the measurement, detect the particle outside the trapping horizon. But for this en route vacuum, once you do a measurement, it collapses to a state which is no longer en route vacuum. So our calculation shows that the result of the detection induces a particle. And you can calculate the location of the particle, and the probability of having the particle very close to the horizon is much, much higher than the probability of it well outside the horizon. So basically, the calculation is done in the standard formulation where you have en route vacuum and the Minkowski vacuum for large distance. You have creation annihilation operators for the notion of particles around the horizon for free-falling observers. You also have creation annihilation operator for particles at large distances. Now, if you carry out the measurement, you can think of a simple model. You have a, say, two-state atom. It can absorb a quantum of radiation, and so you can think of an apparatus with this kind of evolution operator acting on the Hilbert space of both the atom and the Hawking radiation. And when you see the atom changing from the lower energy state to high energy state, the effect on the radiation Hilbert space is to use the annihilation operator to act on it. So basically, you annihilate a particle from the Hawking, from the en route vacuum, and then you get to the new state. So that's what we do. Take this annihilation operator and then act on the en route vacuum. And then using the Bogoliubov transformation equation, you see that it's actually a superposition of one particle states. This doesn't say that you have a particle near the horizon. The operator B would correspond to a particle around the horizon if it's around the horizon. Otherwise, it's just some excited states. But you can calculate the probability of the distribution of this induced particle. And if you detect n particles, you basically get that kind of state from en route vacuum. So then at the end of the calculation, we see that most of the induced particles, they would appear inside the near horizon region. So it's essentially firewall, and they would have particle high energy scale scattering with collapsing nature. So we talked about 3 comments about trapping horizon. One is that there is a gauge invariant Planck scale quantity around the horizon. Second is that the distance between trapping horizon and the collapsing matter is always not much larger than Planck vacuum. And finally, when you detect particles outside horizon in Hawking radiation, you actually induce high energy scatterings of particles at the horizon with collapsing matter. Thank you.
Thank you. Time for 1 or 2 questions. Anyone?
Somewhere in the middle, you said something about the mass decreases not by Hawking radiation, but negative influx.
Right.
I would have thought that negative influx is correlated with outgoing Hawking radiation. You are not meaning that? I mean, where does this negative influx come from?
It's from the vacuum.
And there is no accompanying outgoing Hawking radiation?
There is accompanying outgoing energy flow. So the standard theory is that for the static Boole vacuum, you have both negative ingoing and outgoing energy flux. When you have dynamical collapse, you turn on outgoing, continuous outgoing energy. And the sum of the two is such that the outgoing energy vanishes at the horizon. So they want to say that the Hawking radiation only appears outside the horizon. But of course, when you do the calculation, they are combined together. So you can say that the outgoing energy comes from the ingoing energy.
So you're saying that this vacuum, what you are calling Onlu vacuum, is such that that would be future event horizon. Not, I don't mean event horizon, but apparent. Let me say apparent horizon. Future event horizon.
Right.
You can actually detect particle there.
Well outside the horizon, not at the horizon.
Very far away,
Yeah,
asymptotically.
Like 100 times structural radius.
Right. So that vacuum is same as what Hawking would have used.
Yes, that's what the standard thing they use, I think. That's how you calculate the Hawking radiation spectrum.
That's right.
Yeah. So I'm using exactly the sample transformation coefficients to do the calculation.
Okay, so let's thank our speaker again.